Welcome to the Chem 153 video lecture series. I am Dr. Gil Claudio and I will be the instructor for this course. This video is Module 1-1 entitled The Subject of Thermodynamics. So this is the outline of the entire chapter. It's in your notes. And the reference for this chapter, in fact for the next 3 chapters, the main reference will be Herbert B. Callen's Thermodynamics 2nd edition. The first module for this chapter is called The Subject of Thermodynamics. The objective of this module is for us to identify what we are going to study in this class called chemical thermodynamics. So, for example, one basic example would be if, let's say, we have a beaker and then there's water in the beaker and then there is ice, a piece of ice in the beaker. Outside is 30 degrees centigrade. Inside, probably, let's say the tap water is 20 degrees centigrade and the ice, let's say, it's -5 degrees centigrade. We know that the ice will melt. So if we're looking at the matter, ice molecules will go to the water. Probably some water molecules will freeze back to ice, but very few. Also, when matter goes from ice to water, it also brings with it, although it's not necessarily the only mechanism, but it also brings with it heat. Heat goes in, and probably a bit of heat comes out, but still majority still heat goes in. Heat will also come in from the outside into the beaker, and then also a bit of heat will still go out. And then it's also possible that water can evaporate, but since the water here is colder than the water outside, it's more possible that water from the atmosphere will condense. So as you can see here, what we are going to study is what we call the internal energy of this system right here. When we look at the internal energy of the system, what makes the internal energy change? It will be the exchange of energy in the form of heat. We measure the heat, in this case in terms of temperature. The 20 degrees centigrade will become lower and then the -5 will become higher. There's also an exchange of energy in terms of work. This unfortunately is a bad example for work, but let's just say that this the volume of water actually increases as it increases in temperature, or decreases in temperature. That rarely happens, but anyway, let's just say. Then therefore, once the volume of water increases, the surface here will have to push out the air molecules from the surface. And the amount of energy there, that is what we call mechanical energy, pushing out the air molecules. Lastly, there is now a change in energy, change of internal energy, because of the exchange of matter, as we saw here, the ice melting. And as the ice melts into water, it brings with it it has its own accompanying change in internal energy. So now, what is chemical thermodynamics? It is the study of the interrelation of heat and work with chemical reactions with physical changes of the state within the confines of the laws of thermodynamics. And the energies that we will study are the ones that can be measured in the laboratory. So laboratory measurements of various thermodynamic properties and the application of mathematical methods to study the study of chemical questions and the spontaneity of processes. So chemical thermodynamics is usually associated with a lot of mathematical equations. Now, something about thermodynamics as compared with other branches of, let's say, physics that involve a lot of equations. Thermodynamics neither claims a unique domain of systems over which it asserts primacy, nor does it introduce new fundamental law analog to Newton's or Maxwell's equations. When we say Newton's equations, we're talking about matter that is moving. In contrast to the speciality of mechanics for Newton and electromagnetism for Maxwell, the hallmark of thermodynamics is its generality. What do we mean by that? When we say generality, we say that if, let's say, we are able to derive an equation in thermodynamics, let's say the amount of heat that a certain matter takes in or the amount of change in temperature when it absorbs a certain amount of heat or energy in the form of heat, that same equation is applicable to any form of matter, whether it be air, water, mercury, or hard wood, rock, or foam, something as soft as foam. All of those will follow the same basic laws or the same fundamental laws of thermodynamics. And that's why we say that the hallmark of thermodynamics is its generality. The fact that it can be applied, the same equations are applied to any form of matter. We are talking about equations in macroscopic aggregation. We will see that a bit later. Unfortunately, there is a caveat here which I think we have to understand very well. Thermodynamics does not predict specific numerical values of observable quantities. Instead, thermodynamics sets limits or inequalities on permissible physical processes and establishes relationships among apparently unrelated properties. The thing here is that no specific numbers, instead we establish limits. What do we mean by that? When we say limit, we say at least a certain amount of energy, or at most a certain amount of energy. Specifically, what we are saying is when we have to put in energy for the reaction to occur, we have to put in at least this amount of energy. Or if a reaction is or if a reaction can give us energy, which we can utilize for other things, the amount of energy that we can get is at most this much. Do we know the exact amount? Most probably not. In some cases, yes, but in majority of the cases, no. But we know that it's not going to be above a certain limit. Or when we put in energy, it should not be less than that. So that's what we mean by thermodynamics sets limits. Now, we have what we call intensive properties and extensive properties. By intensive properties, we basically mean properties that do not depend on the amount of matter of the object that we are studying. For example, so this is a bulk property, intensive quantity, or intensive variable. For example, density. The density of water is the same if, let's say, at 20 degrees centigrade, whether the sample of water is a drop of water or a whole bucket of water. Or the temperature of that same drop of water will be the same as if, let's say, we took one drop from a bucket of water. The temperature of that drop of water will be the same temperature as the entire bucket of water. On the other hand, an extensive property is one that is additive for independent, non-interacting subsystems. It is directly proportional to the amount of material in the system. For example, if, let's say, we have very hot water, of course, we would rather that a drop of hot water drops on our skin rather than being splashed by a bucket of hot water of the same amount. We know very well that the amount of injury that we will get from the bucket of water will be much more than just a simple drop of water. The amount of energy there is an extensive property because now it is dependent on the amount of matter of the system. So, for example, here, mass or volume. Lastly, the last main idea here is, in general, the ratio of two extensive properties that scale in the same way, the ratio or the quotient or the ratio is always intensive. Mass is extensive, volume is extensive. The quotient between the two is density intensive. So now, what is this man pushing a crate? Sorry. So if we have a big crate right here, and we have a man pushing that crate, so therefore the man will have to exert a certain amount of force this way. That force is an intensive property. He can put if he's a bit weaker, he can put a smaller amount of force, Once he is finished pushing the crate, let's say the crate is here. So, for example, the man is already tired. He has an aching back and his... Now, we can ask the question, how much energy did the man exert in order to push the crate at a certain distance? Okay. The first thing that we had was an intensive property force. The second variable here, intensive property force. And the second variable here is an extensive property distance. In thermodynamics, the internal energy of a system is expressed in terms of pairs of conjugates. In thermodynamics, the increment of energy transfer is a product of a certain generalized force, which, when imbalanced, cause certain generalized displacement. Delta E is equal to F times Gx, which is basically what we did a while ago. The force that the man placed times the amount of distance is equal to the amount of energy that he expended. So therefore, energy is always a product of a pair of conjugate variables, and the conjugate variables are always extensive times intensive. Since we are dealing with matter which has so many other variables, we can now generalize this equation even further, which is basically the fact that it is a summation of all those. The total energy is the summation of all the different force times energies that is occurring within the system. Now, so if we have a molecule of water, what can happen? How can this water molecule move? The first is something that you may have learned in organic chemistry or even general chemistry, is that the water vibrates along its bonds. Well, sometimes not just along its bond, but along its bonds. The other thing that the water molecule can do is that along a certain axis, it can also rotate. And then lastly, this water molecule can move, so now this is what we call translation. It moves from one place to another. So what do we have? Vibration, rotation, and translation. Okay? There's another thing here. So those are vibration, rotation, translation corresponds to Ke, kinetic energy. Now, we know that water molecule is a usual example because it also is a good example for what we call intermolecular forces of attraction. So this is IFA or IFMA as some is probably more popular way of saying it. But in fact, there's another thing. The chemical bond between the oxygen and the hydrogen is also another force of attraction. So this is a strong force. Strong force, we mean bond. This is, you can say, a weak force. Weak force, we mean chemical attraction between atoms or molecules. Because of all of these, that's why we have solid, liquid, or gas. If we have a lot of motion, contrasted with the amount of IFA a molecule, that matter has. No, all of that is internal energy. We first remove zero velocity, zero angular momentum, and no electric field. A rock that is just sitting in one place. We can say that as long as I'm not going to throw that rock to someone, I'm not going to hurt anyone. But it's not the same if it's a rock sitting on one place as compared to a piece of dynamite sitting in one place. If there's nitroglycerine or dynamite in one place, I'm going to run far away, because we know very well that if, let's say, with just only one spark, that thing will, that piece of dynamite will explode. So in a more dramatic way, we can understand the internal energy of a piece of dynamite. But the rock also has internal energy, although we know very well that it's not going to explode. So all matter has internal energy, even though they are not moving. Where does the internal energy come from? It comes from the previous drawing, kinetic energy and potential energy of each and every molecule. You put all those molecules together, all their KEs and PEs. The sum of all that is the internal energy of that object. So that's why now we can say that atoms are actually repositories of energy. So now, thermodynamics is concerned with the macroscopic consequences, whether water is hot or cold, due to the myriads of atomic coordinates. The motion of water, by virtue of the coarseness of the macroscopic observations, do not appear explicitly in a macroscopic description of a system. Meaning, we are not going to look at each and every motion, or thermodynamics is not going to look at each and every motion of each and every atom in all those water molecules in our beaker of water. No, we're just going to look at the beaker of water. Okay, so that's what we mean by macroscopic, the beaker of water, microscopic, each and every molecule of water in that beaker. We just restrict ourselves to simple systems, which are systems that are macroscopically homogeneous, isotropic, and uncharged, that are large enough so that the surface effects can be neglected and that are not acted on by electric, magnetic, or gravitational fields. A simple system has a definite composition, and with this we are able to include now a variable n. And then we also have what we call the variable v. So now, as you can see, we are introducing new variables. For internal energy, as I'm sure you've already seen in general chemistry, we only look at differences in energy. So that's why we always express internal energy as delta U and not simply as U. Okay? The internal energy, of course, all objects have internal energy U. It's just that we cannot measure the absolute internal energy of things. No? We have to compare the internal energy, or enthalpy even, or Gibbs energy. We have to compare it with a reference system, and therefore comparing it with a reference system is called delta U. And you can say that this is now a mathematical trick. We take the reference system to be arbitrarily taken to 0. But please take note that, so even though we say delta U is equal to that, and as if we are not comparing it to something, we actually are comparing it to something. It's just that we are making sure that that thing that we're comparing it to, we will give it a value of 0. Now, if we look at this picture, we know what's going to happen in a few minutes, or probably even longer, but still, we know what's going to happen. If this is in a beaker of water, ink in a beaker of water, we know that that water will be colored blue after some time. Okay? It's not going to stay in this way. It's staying this. So, we know that after some time it will be colored blue, and we will say that that evenly blue water is now the equilibrium state. We cannot expect that after the beaker becomes completely blue, then the ink molecules will start to congregate again, and go to the other side, go to one side of the beaker, and then part of the beaker is dark blue, the other part is white, is light blue or even clear. No, that's not going to happen. So we are talking about equilibrium. And this is what we study also in thermodynamics. In all systems, there is a tendency to evolve towards states in which properties are determined by intrinsic factors and not by previously applied external influences. Such terminal states are by definition time independent, and they are called equilibrium states. When we say time independent, once they reach the equilibrium state, they never go back. Thermodynamics seeks to describe these simple static equilibrium states, which systems eventually evolve. This is something very important. We always study equilibrium states, not processes. It's just that when we say processes, we are looking at the equilibrium state of the initial and the initial state of the final. We will see that in greater detail in future lessons. Now, with that, we can talk about the first postulate of thermodynamics. We will study in this course 4 postulates of thermodynamics. What are these postulates? These postulates are statements which will serve as the mathematical foundation of all the thermodynamic equations that we are going to study in this course and in your future thermodynamics courses. This is not how historically thermodynamics was discovered. It is more like since since scientists already knew what the equations were, they tried to work out in such a way what are the fundamental equations. The fundamental equations, therefore, from where we base all the other equations of thermodynamics, will be these 4 postulates. The first postulate basically just outlines what we have just said. First of all, there are equilibrium states, number 1. And number 2, we are studying internal energy. And number 2, we are studying the internal energy and the different variables that we have seen. U, internal energy U, the volume, and the mole numbers. The all-encompassing problem of thermodynamics is the determination of the equilibrium state that eventually results after the removal of internal constraints in a closed composite system. Again, what we are saying is we are studying equilibrium states. Now, before we finish, let us define what we call a state function. A state function is a property that describes the equilibrium state of a system. Now that we know that we're studying equilibrium states, we now will look at the property or what we call the variables for this one. So this is what we call state function. So for example, internal energy U is a state function. Enthalpy and then entropy are all state functions. By state functions, for sure they are path independent. The state function depends only on the current state of the system and not on the way in which the system acquired that state. In contrast, we have what we call process quantities, which are heat and work. Unfortunately, sometimes this is also called function or state function. They're not functions as in mathematical functions, but rather they are more like variables. The next one would be an equation of state. We know already the state variables or the state functions. These are variables. We look at how they are related into equations, and such equations are what we call equation of state. An equation of state is a thermodynamic equation describing the state of matter under a given set of physical conditions. It is a mathematical relationship between 2 or more state functions associated with matter, such as its temperature, pressure, volume, and internal energy. With that, we've already defined what are we studying in thermodynamics, and we are already aware that we are going to put them into equations. We will now study next in the second objective how we use those state variables and state functions and create a model in order to be able to study thermodynamics.